Okay, so it's digital signal processing. We're sort of in the middle of lecture 5. And lecture 5 is all about sample domain representations for linear time invariant systems, or LTI systems. And we're just going to continue the lecture. So we talked about finite impulse response systems and infinite impulse response systems. And so an infinite impulse response system is a system whose values, when represented in the sample domain, go on forever. So if you were represented as h of n will have an infinite number of non-zero values if it's an infinite impulse response system. Now, when you're doing infinite impulse response convolutions, and my cursor has disappeared again. Now, I actually tested this out. Yeah, okay, so if I unplug the tablet, plug it back in, sort of comes back, okay. So you write down convolution like this. K goes from minus infinity to infinity, and this, if we keep h stationary, h of k times x of n minus k, and that's the convolution equation that we will be working with. When we do these kinds of, when we try and solve these kinds of equations to get a convolution result, and one of our signals, like h of n, is infinite in length, we have to use, it's almost, we don't have to, it's not always the case, but we very often end up using this relation to calculate the solution. So this is something to keep in mind. And I also mentioned that there's really 3 realizations that we're going to be studying in the short term, and the 4th will come shortly thereafter. There's the impulse response. This is one representation for a system. I can draw a box around it, put x in, and get y out, and I have a system. I can also represent a system as a difference equation, which is just an equation in terms of y and x. So y of n is equal to x of n. Is that a system? Yeah, it's just an equation. On one side is y, the other side is x. Now, I want to point out the fact that this is exactly like the CGR 3111 linear systems. Like, instead of h of n, we had h of t, and that was a representation for a system, right? In the continuous time domain. You also had, instead of equations that looked like this, you had differential equations. So you didn't have, you had differences in y, dy dt, right? For example, dy of t dt is equal to, say, dx dt. All right, and that's a differential equation, right? So it was a continuous derivative that you would have on your values, not just a value of y is equal to x in some form. So the analogy of a differential equation is a difference equation, a discrete difference equation. And so that's what's, so all of these things have analogies from the continuous domain to the discrete domain. Finally, we have the Fourier transform, and the Fourier transform, of course, there is the continuous Fourier transform you studied in 3111. There is a discrete analogy of that called the discrete Fourier transform. And we don't actually get to the discrete Fourier transform for, I see, if you just let it idle for a little bit, your mouse cursor disappears. We're actually going to get to talking about the discrete Fourier transform actually somewhat later in class. So just be aware that we don't talk about the DFT or the FFT for a while yet, because it takes some time to build up and under when you calculate a DFT, a discrete Fourier transform. Okay, so we will talk about difference equations and the discrete time Fourier transform, which is different from the discrete Fourier transform in the coming 2 lectures. So I sort of jumped right into class without, I usually like to offer an opportunity for questions before class. Was there anyone that was hoping or wanted to ask a question? Yeah, and sort of, setting up for class, you sometimes get caught up in all of the technicalities, but yeah, there's always an opportunity for questions at the beginning of class. I like to offer that. So if there is a need, just go ahead and raise your hand and ask a question. Let's see, calculating h of n from system equations. Okay, so here's a system represented as a difference equation. It's just an equation that has y and x in it. And the question is like, how do we get the system from it? Okay. And so when you have a relationship that relates y and x in this way, where there's no feedback terms at all, it's always going to be a finite impulse response, because the way that you get the impulse response, let's remember the definition of the impulse response. What is the definition of the impulse response?
That it turns on that.
It is the output of a system when the input is the delta function, right? So we know that x is the input in our equations and y is the output. So if we want to write down the value of h, what do we allow x to be? The impulse response is defined as the output y when the input x is equal to the delta function. So how hard is it to solve for h of n for this equation right here? If we just apply that definition, what do we let x? We let x of n equal what? Delta of n. So then what is x of n minus n naught? And so if we let x of n minus n naught equal delta of n minus n naught, what comes out? The system as an impulse response, or h of n. So you can simply write down h of n is equal to y of n when x of n is equal to delta of n minus n naught. We didn't even actually do any work. But what we did do is we used the definition of the impulse response. And we said, all we have to do is let x equal the delta function, then y is the impulse response, and the impulse response is the thing that we call h, right? That's all that we've done. So this is exactly like saying the output of the system is going to be whatever comes out if you let the input be the delta function. Well, if you let the input be the delta function, that's setting x of n to delta of n. If you have x of n minus n naught in your system, like as your representation, that means that you have to put an n minus n naught wherever you would have an n. So you have delta of n minus n naught, and there you get this. Similarly, you do the same exact process for this difference equation. You get this as h of n. H of n is equal to delta of n plus 1 minus delta of n. Essentially, what you're doing is everywhere where you're seeing an x, you're substituting a delta. Now, this will only work when y of n, there's one term in y, right? Now, if you have another term in y, then there's feedback. If the value of y of n is a function of other values of y, you cannot do this. So this is only for FIR filters. When there is feedback, it is an IIR filter. So you cannot apply this. Say you have y of n minus a y of n minus 1 equals x of n. You can still apply the property. Let's let x of n equal delta of n. And then you have y of n minus a y of n minus 1. And then, but what happens here? It's no longer for operation. For example, what is y, assuming that y of minus 1 is 0, what is y of 0? Y of 0 is equal to delta of 0, which is 1, plus a times y of n minus 1. So a times y of n minus of y of n minus 1 is y of minus 1, right? So that's actually 0. So it's a times 0. So it ends up being 1 plus a times the number 0, which is equal to 1. All right, so then y of 1, now we start to see that things are not all of a sudden change. It's not explicit. Like now y of 1 is actually 1. It's 0 for the delta function. That's delta of 1 plus A times Y of 0, times Y of 0. And Y of 0, that's A times 1. So now it's A, right? And then Y of 2 is going to actually be, it's going to show you that there's a recursion happening. It's 0 plus A times Y of 1, which is A times A, or A squared. And as you can see it, now you're actually going to get Y of n. It's going to be, for any n that's greater than 0, it's going to be A to the n. It gives you this output gives you Y of n equals A to the n U of n, and that's equal to H of n. And so that's a totally different kind of problem, right? And that's because there is feedback, right? It's because there is feedback. When there is not feedback, and there is no other terms in Y, and you can just substitute deltas in for X's, and you will get the impulse response, right? Any questions? Yeah.
Sorry, I missed it, but which of these was the finite impulse response, or were they all finite?
All of these examples here are finite. This one example that I did right here, this is not finite because it has a feedback term, this Y of n minus 1. And so none of these equations here have more than one term on the left-hand side. They all have just Y of n. So I took an example where I have two terms in Y on the left-hand side of the equation, or just in the equation at all. And when you have more than one term in Y in your equation, you do not have a FIR filter. Your H of n is not finite, and you have to use other means you have to use the methods for infinite impulse response filters to get the impulse response. Okay. Calculation of H of n from system equations. So I ask the question, what types of filters are the systems below? Are they FIR systems or IIR systems? So in this case, we have Y of n is a sum from minus infinity to n of x of k. Is that IIR or FIR? Okay, so let's see. So in the process of this, we let x of k equal to delta of k, right? And we have the equation H of n is equal to the infinite sum from minus infinity to n of delta of k. How many discrete values is in H of n? No, but how many values? Like you can't, it's going to have values at the values of k from 0 to infinity, but how many of those values in total are there? Okay, so let's go back to the question. Is the impulse response infinite or finite? This is infinite because in fact, this impulse response is actually U of n. U of n has an infinite number of non-zero values. So this is an IIR filter. Now the moving average filter. Now we're going to assume that M1 and M2 are less than infinity. They're not infinite. Okay. So under that circumstance, we have this input-output relationship. So for this input-output relationship, we have this sum that goes from minus m. So we'll also assume that M1 and M2 are greater than 0, so that the sum is not kind of is greater than 0, so that the sum is kind of easier to analyze. So M1 and M2 are greater than 0. So that means we're starting from some negative number, like minus M1, to some positive number, M2. And how many terms are going to be in this sum then? Like to say if we went from -1 to 1, how many terms would be in there? 3. There'd be -1, 0, and 1. And so what if it went from -2 to 1? It'd be 4. In fact, it turns out that this actual denominator here is the number of terms, and that's why it's an averaging system. It's just taking like M1 plus M2 plus 1, because that's the 0. It's got to count 0. M1 plus M2 plus 1 is the number of terms that are in this summation. So say you were trying to sum over 3 terms, you know, and you need to divide by 3 to get the average, right? So this equation just says, okay, take the current value of x, which is x of n minus, you know, the future values back to m1 or and past values back to m2, and take that region and average all those values around 0, so to speak. That's what it does. So that's what the moving average system does. They use this a lot. I mentioned this before, but they use this a lot in stock market analysis. I hear the stock market's not doing so well these days. So the moving average actually responds slowly to that. Like if it was doing quite well last week, and it just starts going down this week, it'll actually keep going up until the number of negative values dominate, and then it will go down, right? And so, you know, the moving average is sort of a slowly varying curve that kind of lags behind and follows the trends, but doesn't immediately respond to instantaneous values. So someone mentioned that that's a low pass filter. It's not going to follow high frequency or daily variations. It's going to actually follow much lower frequency or trends in the data. So that's what a moving average does. Yeah.
Is this a similar definition to like stability in the system?
So stability would be more, so you can analyze this system for stability, but in general, when we talk about systems, it's like any one of these equations can either have it or not have it. So it's like a yes or no. And so it would look at this and say, okay, this system is an average. An average is always going to be lower than its maximum value, right? So you can say that, you know, like I can guess kind of straight away that this guy's going to be stable. So it's always a question to have, but so anytime that you look at something that involves X's and Y's, you're gonna, that means you have a system, and then the property is kind of like an evaluation of it. And the thing is, like when we use the system properties to kind of understand the character of what we're analyzing. You know, if you know a system is unstable, you've got to be very careful about making sure that you operate that system in a domain where it's not going to explode, you know? And that's kind of how we use the properties in practice. Any other questions before I go on? All right, let's talk a little bit about how we break down a signal. So you can take a function X and break it down into a sum of delta functions. That's what this is, right? And so in this case, we've got a function that has a non-zero value at n is equal to -2, a non-zero value at n equal to 0, and a non-zero value at n equal to 3. And so we'll write the non-zero value at -2 as x of whatever its actual value is. We'll call that x of -2 times delta of n plus 2, which is the delta function that occurs at that location. So times 1, but that 1 only occurs at the index n equal to -2. And then we can write the value of 0 similarly as the actual altitude, this value x of 0 times the delta function that occurs only at 0. And then we can write it as x of 3 times the delta function that only occurs at 3. And so if we were to write this function, we can write it as the sum of 3 delta functions. So we're going to reuse that concept later because now we've got these 3 delta functions. This is the same function that we had before, but now we're going to be convolving it with this function. And this function is our representation for a system. Now we're going to write it down. So it's a linear time invariant system. It is a true statement that any linear time invariant system can be represented by an impulse response. There is an impulse response that represents any linear time invariant system. So and every linear time invariant system, if you have it written as a convolution, you know already that the system that is represented there is linear and time invariant. Convolution represents linear and time invariant systems. So if a system is written as h of n, it has to be linear and time invariant. because it's actually plugging into the convolution equation. And the convolution equation is a representation for all linear time invariant systems. So it's kind of an oversight, but it's important to know that as soon as you talk about an H and an H of n, an impulse response, it is a linear and time invariant system. Okay, so here is the convolution equation. In this case, we're taking x sort of fixed in k, and we're shifting h for different values of k. All right. This star, you've seen it before. Usually, kind of see it like x of t star h of t, and that sort of gives you y of t. Just like, but this denotes convolution. And I don't know if you folks remember the equation that you had in 3111, but it kind of looks like this. You go from minus infinity to infinity, x of tau, h of t minus tau, d tau. And then you write that as y of t because you're integrating over tau. Tau goes away, and you got a function that's only depends on t. Because when you integrate over a variable, it's it doesn't show up after the integration. You've removed it's no longer present. So tau goes away, and you have y of t. Okay, so that's the same thing that's happening here. We have this summation behaves just like that integral from minus infinity to infinity. The product that you have inside the summation is the same product, but now we're only evaluating it at discrete values, at integer locations. N and k are both integers, right? So this equation operates in every regard very similar to the integral. You do integration different from summation. That's very true. And we'll find out what the trick, there's tricks, like you integrate the exponential function, you got to remember what to do. You integrate a polynomial like x, you got to remember what to do. You got to remember your calc 2, right? This exercise is I think you have a geometric series in calc 1. So this is harkening back to your freshman year when you learned how to do geometric series. That's the tool you need here. That's the tool you need. All right, so let's think about, yeah.
I was just gonna ask as a reminder, when we look at this graphically, isn't the convolution where you like slide the impulse response over?
Yeah, you can think of it as, so if you look at this as so a lot of times people like to explain it as minus k minus n, like as h of minus k minus n, right? And so you can say you're taking h of k minus n and time reversing it, then multiplying it. So you delay h of k, you time reverse it, and then you multiply it value for value against x of k and add up all the results. So that is actually what's happening. Students very often say, that sounds great, but it's extremely confusing to them often. So we're gonna talk a little bit about the graphical, we'll talk about the graphical model, we'll talk about the mathematical model, and then we'll talk about the methods for solving for discrete functions, and that's sort of the way that I approach it. So we'll cover that in a graphical representation. So okay, yeah, you bet. So we have this representation over here. We sort of, on the previous slide, we wrote this function here on the left as x values multiplied by delta shifted, but now we've got this new collection of values here for h of n. So how does this all work? Well, you can think of it as if we were to write, so we wrote it like x of minus 2, we wrote x this way. I'm going to write it all out because it's kind of never written out. Delta of n plus 2. What will be the next term? Well, that's at 0. So it's x of 0 is the value at index 0. And delta of n restricts that value to only occur at index 0. Otherwise, it's just a constant, exists forever, right? Exists for values 1, 2, 3, all of them. The delta function restricts the value to only occur at index 0. By multiplication, because it only multiplies by 1 at one spot. Okay, so I've lost my cursor. That's okay. I can overcome you, technical problem. It's going to innovate and mess things up again. So now we've got There's a value at 3. So x at 3 is the magnitude of the function at that index, and we multiply that by delta of n minus 3. So this is how we might write that function x of n, right? X of n is this. That's how it's sort of written mathematically. And so if we were to plug that x of n as an x of k into our so x of k would look like x of minus 2 times k is delta of k plus 2, right? It's just a k wherever there was an n, right? And so then if we plug that x of k back into the convolution equation, we end up with a bunch of shifting property integrals. And we see that all we're doing is taking the function h of n and sort of shift and amplifying it. So let's look at just the value here at this index at minus 2. All right, we would write that value like this. And if we take x of minus 2 times h of n plus 2, so that's a delta of n plus 2 convolved with h of n is equal to h of n plus 2. So we're using the shifting property there. We'll kind of verify this over and over again. And so that means that we're just taking h of n and we're shifting it to where this delta function occurs, and we're amplifying it by minus 2. So that's what one delta function will do. So this way we're talking about convolution as we're doing this at every single value where x has a non-zero value. So the actual convolution ends up being, well, that sum that we just saw, this function here, that's the function that we get from this value in x. Then we consider the value at 0. We get this function when we do the convolution for that value. And then we get, when we consider the value at 3, we get this function, because in this case, x of 3 was negative, so it flips h to be negative, and it occurred, now it starts at x of 3. And so then what we end up doing is adding together all of those signals. When we add together all 3 of those signals, this is the signal we get. And that is the value of the convolution. Okay, so what's the key idea there? We're taking the function, one function h, and we're shifting it to wherever the value of x is and amplifying it by the value of x and then adding it back into itself, right? That's what the operation is. Any questions on the this presentation of the graphical convolution? Yeah. Why? Oh, is this way back where I was doing A? Yeah, this one here. Okay. Y of -1. Is this one here? Y minus 2. Yeah. Right. Yeah. Y of -2 is going to be this entire function here, but it's actually going to start at -2 where this is here. So that's so they have this weird subscript to kind of explain it piecemeal. And so it says it's basically we're taking this function here, h of n, and we're placing it such that it starts. This would start at 0, but it ends up starting at wherever the value of x is, which is -2. And then the value of x actually scales it. That value of x at -2 ends up amplifying h. So the way that they write h shifted to be at -2 is they write it as h of n plus 2. So h of n was this signal was h of n just at 0. So we write this signal shifted to the left by 2 values is this h of n plus 2, which is, so it's been advanced, so to speak, or shifted to the left. Yeah, I think there's a value 1 that's kind of hidden by my I kind of wrote right over it. But yeah, and there is no, like, there is actually no specific value specified for x of -2. So it's not like, it doesn't have like a 3 there or anything. It just like, I could put a number here, a, and since h is 1 here, this would be the value a, right? Just to clarify what the amplitude actually is. And if this value were not 1, say that the value were a again, it would be a squared or something. You see on this, just to be clear? Yeah, yeah.
Were we given the HFN or did we derive that?
H of n is just going to be a system. So every system will have a different H of n value. This one's just an example to kind of, you need some kind of graphical example to write down just to kind of see how it works. But H of n is, H of n is totally generic. Okay, so if we were to write all that stuff down mathematically, it would look like this. So here is our representation of the impulse response in terms of a sum of delta functions. This is a different way of writing x of n. It might look confusing, but it's just saying you can do it. You can write x of n as a sum of delta functions where every value of x is just a scale, a scale factor on some delta function. That's what's there. So if you apply a system, okay, and it's still there. So, all right. Good. So if we apply a system here, this system to x of n, we represent that system as a linear time invariant system using the convolution operation. And so that involves a new character, h. And so this is how we write that LTI system. Now, in this slide, I point out a property. This is a properties of LTI systems slide. So now we're talking about what kind of properties LTI systems have. LTI systems are commutative. That means that if you take X and you input it to a system H to get output Y, an equivalent output would be gained if you took H as the input and input it to the system where X was actually the value of the system. So X convolved with H is equal to H convolved with X. That makes sense? Yeah.
What about when you're talking about with the feedback systems? Where you kind of had a, I might be getting ahead of myself.
No, that's, we will get to that. We'll get to that, but it's good to ask that here. But it actually satisfied irrespective of whether it's a finite length or infinite length. It's always true. Yes. Any other questions? All right, let's do a finite length convolution. So there are probably 7 different ways to calculate a convolution of 2 discrete finite length functions. I will teach you one way to calculate the convolution of 2 discrete functions. This is the way that I've taught, well, probably 4 of the 7. There are a couple actually that come from overseas that I just don't think would be, be good for students. Like Chinese ones, they actually read up and down, right? And so your convolution table is like different, and they go right to left, and some nationalities like to some diagonally. So I've omitted. I never taught any of those. We're gonna do the one that over the 17 years I've taught this course that has maximized student grades. Okay, and that is the following procedure. You have 2 finite length functions, all right? Here is finite length function number 1. There's 2 characters in convolution. There's an X and there's an H. And then you your goal is to calculate Y, okay? X is one of those characters. I've decided in this case to list X as a sequence of values and an interval for n from 0 to 4, where these values for the interval are where the function actually starts and actually ends. It has a non-zero value at 0, and it has a non-zero value at 4. So that's the n is greater than or equal to. That means it actually there. So there are 5 values in this list of numbers. And there are 4 values in this list of numbers. And this is how I represent H. And the procedure for doing the discrete convolution is as follows. You make a table. This is called the tabular form of convolution. On the top row of this table, you put X, and you simply write down its values. You need not have values for n. I write these values for n for our reference for the first time that you learn this if you have not seen this before. But in general, you do not need to write them down. I'll show you why in just a moment. But we're writing them down here so that it's clear. Then you write in the next row the values of H. And so H has values 1, 2, 0, and -1. So we put them all in corresponding columns. Right? Now, if they had arbitrary indices, we would just put the first value and then all the other values in a list there at the top. This row is sort of optional. And we'll find out on the next slide. So then what do we do? The first operation we do, so we're going to end up calculating as many rows in the table as there are values in H. Okay. And so if you want it to be faster, if you like your tables wider than they are, more columns and rows, you can flip X and H. Why? Because H convolved with X is equal to X convolved with H. So you can flip the two rows if you like your table to be different. But I'm going to teach it this way, but we all know that it doesn't matter. You can flip X and H, and all you have to do is make sure you list your numbers in so-called English order. The number on the left goes on the left, and the number at the end goes on the end, and you start you list them. Okay, so the first row that you calculate is you take H of 0. That's the first, in this case, whatever number is in the first column of the second row. And you multiply it by the entire first row, and you write down that multiplication in every column. So 1 times -2 is -2. 1 times 0 is 0. 1 times 1 is 1. 1 times -1 is -1. 1 times 3 is 3. And we get this row. Then we stop. The next row, we do something very important before we start the process. Again, we insert a 0. Why do we insert a 0? We're actually going to be delaying, in this case, X by 1. So our output actually starts at the next index of n, not at the index we had before. All right. So we're going to take H of 1, which is this value here, and we're going to multiply it by X again, but by starting in the second column, it's really X of n minus 1, right? Because we've shifted X one time sample or one sample index. So we take 2 times -2 is -4, 2 times 0 is 0, 2 times 1 is 2, 2 times -1 is -2, and 2 times 3 is 6, and we get the second row. Now, all the red values that you see in this table are the result of these 0 insertions. Every row that we do after the first row involves the addition of another 0. Now we have 2 zeros inserted, and we do exactly the same process. We take this value here, 0, and multiply it by the values of the top row. I know what this row will be. This row will be zeros. So I just go ahead and write a row of zeros. Now, if you have a row of zeros in a table and we're going to end up doing a column sum of this table, you actually don't even need to write this row. But I often encourage you to write it nevertheless, so that you keep your numbers, like you always remember to put in the zeros. If you omit this row, you might actually forget to insert 3 zeros on the next row. So I always suggest, even if you have a row of zeros, always write it in. Okay. Next row, we now insert 3 zeros into the front, and then we take this number, -1, and we multiply it by all the values in the top row. So -1 times -2 is 2, -1 times 0 is 0, -1 times 1 is -1, -1 times -1 is 1, -1 times 3 is -3. And we have finished the calculation of our table. Calculation of our table is this green region. That is the calculation of the table itself. To calculate the convolution sum, you sum the columns of this table. So we sum this way and we get -2. We sum this way, we get -4. We sum this way, we get 1. Sum this way, we get 3. We sum this way, we get 1. Sum this way, we get 5. This way, 1 and -3. And this is the convolution sum. That is the result of the finite impulse response convolution. Now, why is that the case? Well, what was the first row? It was H of 0 times X of n. That was the first row that we calculated. It's this number, which is H of 0, and then we multiply by X of n. What's the second row? So that's what I have written in the side here. What's the second row? It's H of 1, which is the second number. And then we took X of n and shifted it to the right by 1 sample. So it's H of 1 times X of n minus 1. Right? We delayed X. So that's why I've written this mathematically in the second row. That's what these numbers are represented by mathematically. and then this for the third row, and then this for the fourth row. Now, if we look at this as a sum and we represent it as a finite sum, it's the sum from k equals 0 to 3, h of n, x of n minus k. So it is in fact the realization of the convolution equation in a table form. Because this equation on the left here is in fact the equation that is the convolution equation. More generally, so it's this equation right here. Why is this sum not going from minus infinity to infinity? Because I know that there's no value, h, when we look at h, which is static in time, h is only defined from 0 to 3. So all other values of h of k, for any k that is not between 0 and 3, the value of h of k for all of those indices is 0. And what that means is that all of those terms don't exist. They're all 0 valued. So the only terms that we need to calculate here are the terms for which k takes on the value 0, 1, 2, and 3, which is why this is the convolution sum. So you got a question first. Cannot use this. That this is, so by the way, I'm going to show you so this is FIR convolution. There's a slide IIR FIR. So if you have one is IIR, the other is FIR, you use this. And then finally, last slide is IIR, IIR. So 3 possible contexts, but 4, X and H can be, there's actually 4 possible cases. But the second case comes up twice because they're symmetric, right? If one of them is FIR and the other is IIR, there's 2 such cases. X could be FIR or X could be infinite, right? And the other is, yeah. So we'll come to that. But you cannot use that. This is for FIR, FIR. And we notice that, both X and H are finite length here. Only in that context can you use this, yeah.
If you would change n minus k inside h, if you also choose the boundary from
So yeah, you would go from 0. Yeah, if you swap to X and N, yeah, it would go from 0 to 4, and then you'd have more. So instead of having, so in this case, we had 4 rows and we ended up having 5 columns. You would have 5 rows and 4 columns. Does that make sense? Yeah, that's how you get the same numbers. You might want to even try it just to check. But one other thing, we noticed that if we do a convolution and it involves, this has 4 values and this has 5 values. If we have a convolution where one signal is length m and the other is length n, the output will be m plus n minus 1. All right, so in this case, it was 5 plus 4 minus 1, or 8 values on the output. So there's a question over here? Yeah.
You have some, let's say H negative and indices defined.
Yeah, and that actually, let me talk about that, because that's actually my next sentence was about to be about this thing up in the right actually addresses the fact that all you need to know is where they occur. So as long as you write down this, and then after that, we'll see if there's still uncertainty. So in general, if X of n is a signal with first and last non-zero values occurring at NS1, that's its first non-zero value, and NE1, that's its last non-zero value. And H of n is a signal with first and last non-zero values, and S2, that's the index where H starts. It is non-zero at S2, at N of S2, and ends at NE2. Then the signal Y of n starts at index NS1 plus NS2. You just add the start indices. What are the start indices for this? 0 and 0. What is the start index of the output? 0. It's like, isn't that lovely? The simplicity is beautiful, but you must be aware of the definition. It is where the signal's first non-zero value is. If this inequality were written as just a greater than, you don't use 0, because the first non-zero value is the next value of n, right? So just be careful about that. No, just bear with me. Now, the last value of this signal, we look at the last value here, 4, last value there. What's the last index of that is non-zero in our output? 7. 7. Is that right? Well, this is 0. This is 7. It better be right. They should fire me. Oh, I gotta be careful about that. There'll be instances where I slip up, but this one is not one of those instances. Anyways, the final analysis that always works, and it's so simple. It's like that's why I so strongly suggest you use it. But you do have to be able to identify the first non-zero value of both x and h, and the first and the last non-zero value of both x and h. So do you have a question?
Oh, I was wondering if,
Yeah. In fact, the conv. Let's go ahead and let's just go ahead. Yeah, we can just open it up and type in the numbers and just type conv and then it comes out. But it's always good to know how to do it as well. But let's see. So there is a function conv, help conv, and of course this is actually microscopic. Can you folks read this? No, you cannot. Okay, so can you read that? Okay, so we're gonna hope that MATLAB decides to talk to me at some point. Okay, so convolution and polynomial. So it turns out that you can actually multiply polynomials using convolution. It's actually the same, but who cares? So conv of A and B. So conv of A and B gives you C. So we're gonna write down a vector A and a vector B. So what's our vector? Oh, can I just write? Okay, so conv. And so what was our first vector? Well, we'll go back and have a quick look. -2, 0, 1. -2, 0, 1. -1, 3. Okay, that's wonderful. Thanks for the assistance. So the H is 1, 2, 0, and -1. So notice I'm forming vectors 1, 2, 0, and -1. And so then now MATLAB will never give you the right indices, by the way, because MATLAB is only one based. You can't even represent the index -1. Like you can't write a function of. But this is the values, and so we go over here: -2, -4, 1, 3, 1, 5, 1, 3, and we see that we get this. There's a -3 at the end. So you get the same numbers, right? And if we were to kind of swap things around, just to kind of verify this commutative property, you can certainly do that. And you see that you get the same result. And so MATLAB it's good. It's a good tool, right? It's got this stuff right there. You can just call conv and check your answer. So yeah, this stuff is in MATLAB. And you can also you can actually write it as a program. For I goes from you iterate over k and all that. So is that all right?
yeah, I was just wondering,
Sure. Yeah. If you want, in fact, MATLAB can do many of the exercises. Not all of them, but you can always go and verify it. And MATLAB can be a real utility to you, given that it's accessible to you during both examinations and quizzes. So, expertise in MATLAB may help you. So, any other questions? Yeah.
What does the E in the S represent in the convolution?
Sort of the end index. So like remember the S's indicate we're taking the start index. So I'm just trying to remind you that the value, like there's so many variables here, right? Just trying to remind you that this is the start index. So you have to add the two start indices, and the E denotes that it's an end index. So you can't add 0 and 3. It has to be the start.
And then, is there a way to work backwards from the MATLAB output to get what your starting index was?
You can, so I don't know what that means. You can, so in MATLAB, in general, let's just talk about how to do discrete signal processing in MATLAB. In general, when you're processing discrete signals in MATLAB, you need the signal, and then you sort of have to have the indices for the signal at the same time. So you kind of like, if I were to write that signal for h of n, this went from 0 to 3. So I'd have to have a vector like h n, or so n values for h, and I would list it as like 0, 1, 2, and 3. And so now I've got the n values where h was defined. And if I were to plot h correctly, I would do stem of the x values where those are the n values of h, and then the actual values 1, 2, 0, and 1. It's the only way you can actually get MATLAB to give you the right stem plot, because otherwise it'll just, so that's right. That's what it is. There's a circle here, a circle there, and a circle there, and the other one's at 0. So that is the actual correct plot. But if I were to just plot it without having that separate vector to bookkeep for all the indices, it wouldn't actually be the right function. And I'll show you that if I just were to call stem without that separate collection of values of n, well, then all of a sudden, well, where is it? Is it under plots? Well, no, why would it be there? Maybe it's over here. Okay, so see it starts here, starts plotting at 1, because MATLAB understands the first value in your vector to always have index 1. So it just uses the natural ordering of the vector, and it puts a 1 in there, which isn't actually the correct plot, right? So as a rule, for sure you can use the indices, right? And you can take the first value, like if you do the bookkeeping where you put that first value at the front and the last value at the end, you can write a program that says h of 1 plus, x of 1, you know what I mean? And you would get the right result. But you kind of have to do all the bookkeeping out, as separate variables in MATLAB. Does that help? Yeah. Okay. All right. Can we reverse the rules? So this is kind of to your question here that like we kind of flip it, but now we have 5 rows, and we just do out the calculation. So I'm not gonna, my arithmetic's terrible for one, and I'm sure that your arithmetic is much better. So I'm not gonna actually repeat all of these multiplications and rows and all of that. But this is in fact comes out to the same values, and we sort of already verified that in MATLAB. We kind of talked about it as a mathematical property, and now we're sort of showing that it's also true. It does not, you can't go wrong with the table method if you just apply the process. It doesn't matter, as long as one of those 2 rows are your 2 functions, and you use the for the indexes, you use the concept that it's really where that first non-zero value is, then you'll be all right. All right. Convolution problem number 2 and 3, if you were looking at all 4 permutations, is that one of these signals is infinite in length and the other is finite. So it's called IIR, FIR convolution. That means you're convolving one infinite length signal with one finite length signal. This is a signal. Is it infinite in length or finite? It's got a U of n in there. That means it exists from time 0 onwards. This guy is infinite length. How about this guy here? That's finite for sure. I can count the values, and there are 5 of them because it goes from 0 to 4, 0 inclusive, right? So it means there are 5 in total. Let's do this. So it's time to get out your math skills and get out your geometric sum and get out your preparedness to apply the geometric series. As I indicated in the past, I warned you this is coming, and it has now arrived. We are going to use math. We are going to use this geometric series sum, and this is how we're going to do it. All right, so first of all, we take the convolution equation. This is the convolution equation. We have a value for h, we have a value for x. Whichever one of these 2 entities is infinite goes in as the fixed part, the one that's not shifting. Okay, it's not shifting. So this one is the infinite part, 1/4 to the n u of n. So I put it in as the first part. So this is h of k times x of n minus k. That's why I selected h as the stationary, the non-shifting component. Otherwise, you have to deal with shifting exponents, right? N minus k is in the exponent. It's a more complex algebraic manipulation. It's the same answer, but more pain. All right. Now, what do we do here? Well, we look at this and we say, okay, this is an infinite length signal and this is a finite length signal. And in fact, we can write out x as a sequence of delta functions like we've mentioned in the past. There are 5 values for x. 1, 2, 3. Am I missing a value here? Oh, right. One of the values is 0, so that value dropped out. So there is no delta of n minus 1 in this sequence because that the value of x there is 0. So we don't need to actually, it's 0, so it's not going to end up affecting the sum. Then we do the convolution. We do h convolved with all these delta functions. So h convolved with x is equivalent to h convolved with minus 2 times delta of n, h convolved with delta of n minus 2. So we have lots of different convolution problems. We have, in this case, 4 convolution problems, but they are all simple because they are sifting convolutions. A sifting convolution, if you take x of n and convolve it with delta of n minus n naught, what is the result? X of n minus n naught. So essentially, whatever you're doing, this term here gets put into the argument behind n, whatever it is, right? And we've done the sifting sum, and we'll end up doing it over and over again. But I'm just going to say that's mathematically what's occurring. So we have 4 such instances. So we can just write down this thing. This is going to equal minus 2 h of n convolved with delta of n. What is that?
Want to be -2.
So I'm going to write, well, okay, so it just disappeared again. So if h of n convolved with delta of n is equal to what?
Gonna be y of n?
It's just h of n again, right? And so in this case, the n naught has the value 0 and x is equal to h, right? So this is just equal to h of n. So it's -2 times h of n, right? Because it's -2, that's a scaling property, and by linearity of convolution, and we can just put that in afterwards. And then we have h convolved with delta. H convolved with delta is just h. All right, what's h convolved with delta of n minus 2? Plus h of n minus 2. What's h of n convolved with delta of n minus 3? There's a minus sign out in front, so we have to be mindful of that. So it's minus h of n minus 3. And then what's h of n convolved with delta of n minus 4? H of n minus 4. So there's a 3 here, so we have to note that. So it's plus 3 h of n minus 4. And we just did that convolution. Was that scary? Maybe a little bit, but we go to the sifting property, we exercise the sifting property, and we come out unscathed. So there's a sifting property based problem. All right, that's what I'm suggesting as your solution. Now we know what the form of h of n is, right? It's right here. It's just written down. Now it's just substitute. So -2 times h of n. That's -2 times 1/4 to the n u of n. That's our first term. So h of n minus 2. Well, it's 1/4 to the n minus 2 power u of n minus 2. And that's this term right here. Then we have minus h of n minus 3. Well, -1/4 to the n minus 3 power u of n minus 3. And then finally 3 h of n minus 4. That's 3 1/4 to the n minus 4 u of n minus 4. And so we get this wonderful little function down here. And it seems like it might be complicated, but it doesn't need to be. All we're just doing at this point is plugging in. So that is my suggestion for all pairings of finite impulse response functions with infinite impulse response functions when calculating convolutions. Any questions?
Yeah, I have a quick question.
Yeah.
So, what if we would have had like n over 4 to the n power? And we would have done like n minus.
So n over 4 to the n power is actually not, is that a time invariant function?
No.
No, so you can't, so it's not an h of n. But it's a good question.
Okay.
That was a brain teaser, but thankfully I don't have to answer it. Just say. But there are situations where you can represent functions as n times, and you just have to go. You just have to go and try and solve it. you can't really represent the system as a linear time invariant system. In this case, it's not linear.
Oh, I
Yeah.
see what you're saying.
Yeah. You got a question?
You only gave us the MX formulas for with any zero.
Mhm.
Do we not deal with any of negative signs?
Yeah, in fact, you can deal with any start index. And so what you can, there's two ways to approach that. You can take the arbitrary start index and move it to 0. So if it's say that this were to start at 1 and not 0, then this is this, you get this. Why does this happen? This is my life now. Okay, so this plug and I are gonna be friends. Okay, so if say that we're to start at 1 and not 0, that just means you get the same sum, but that 0th term isn't there, so you have to subtract it back out. So you get this thing, whatever it is, and then you subtract whatever a to the 0 power, which would be 1. So you'd be subtracting a 1. And so you can like reapply it and then just kind of subtract out the terms that you don't have. It's one way to do it. That just is essentially one approach. And that's quite equivalent if you were actually to take what would be the mathematical approach, which is actually choosing a change of variables. So if you were to wanted to start, say this thing started at, I don't know, 100. And so k, you want the sum, k goes from, I don't know, 100 to infinity, something like that. So you would write, you'd want it to be start at 0. So you define a new variable. So it's m is equal to k minus 100. And then you'd rewrite the entire equation in terms of m. And so when you plug it, so then that means that k, so when m is equal to 0, k is equal to 100, right? So so all of a sudden, now when you rewrite it, the sum starts at m equals 0. And you still get when k is equal to infinity, when k is equal to infinity, m is also equal to infinity. So you still get, now your sum starts at 0 and goes to infinity, but like you have to cope with that substitution in the actual formula. Like if it was 1/4 to the n, right? So then it would be 1/4 to the k, right? And so you have to solve for k. K is equal to m plus 100, right? And so it would look like this. It would be 1/4 to the m plus 100, right? And then this is a u of k. It would be u of m plus 100, right? And so does that make sense? Yeah, so you kind of, that's what they call in mathematics a change of variables, and allows you to change that equation to be whatever you want it to be in start index or like end index. And finally, there is a formula that starts at an arbitrary index, M1, right? And M1 can be negative, and goes to an arbitrary index, M2, which is finite or infinite. And there's a formula for that. And I think I give that to you in a slide, not quite on this slide, but and you can use that formula for any finite sum over any finite index, or you take its limit. If you're going to negative infinity, you take the limit as if one of the bottom limit were going to negative infinity. If it goes to positive infinity, you take the limit of that equation. And so it actually, if you have that general form, it addresses every possible sum, starting at any possible index and over any infinite or finite interval of indices. Does that make sense? And so if you never want to have to worry about, this summation equation, you go to that one and then know how to take its limit. Okay. All excellent questions. Any other questions before we go on? All right, we're going to finish discrete convolution today because the last possible form of a discrete signal processing convolution will involve two characters, x and h. And those two characters will both be infinite in length. So we can't simplify life by just assuming that we're going to take the static version and make it the infinite one. We actually have to do more work. So there's no way out of it. We have to look at all of the bounds and calculate the interval of integration or summation, and then apply that knowledge to calculate the output. So h of n, this is its form, same as we had last time. It is infinite in length. X of n, this is its form, 1/3 to the n minus 1 u of n minus 1. It's infinite in length, starts at n equal to 1 and goes on forever after that. All right, we need to apply the convolution equation. This is the convolution equation. And the first thing we always do is plug in our values. 1/4 to the k u of k, 1/3 to the n minus k minus 1, because we're plugging in n minus 1 for n. So we would do n minus k, but n itself is n minus 1. So we end up with n minus 1 minus k, or whatever in here, which is n minus k minus 1. It's the same equation, right? It's the same thing. And u has the same form, u of n minus k minus 1. Now we have to ask ourselves some difficult questions and re-exercise the methods that I've told you before about finding out when a function is equal to 0 and when that function is equal to 1. We want to figure out how to simplify these limits of integration so that we end up with a simpler integrate sum. And we want to apply our finite or infinite lengths. You know, like if it's doubly infinite, it's going to be hard to evaluate. I mean, ultimately, we could sum from 0 to negative infinity and from 1 to infinity and do a doubly infinite sum. But almost none of your convolution problems will be like that, because almost all of your convolution problems will be unstable if you end up with a sum like that. Has an infinite number of values, and there's a doubly infinite sum. Even if it's negative and positive in places, it's usually going to explode. Right? Usually that will be explode. So you usually will simplify it to a one-sided sum. You will either sum out to minus infinity and the other side will be 0, or it'll sum out to positive infinity and the other part of the real line or the integers will be not part of the sum. So my first argument here, or my first suggestion here, is to simplify the bounds. And so we want to simplify the bounds of the summation, or if you were to do a convolution, you would summation the interval of integration. So we look at this function here, u of k. When does it turn on, so to speak, and when is it all on after that? U of k turns on. Is this actually happening to me? It turns on when k is greater than or equal to 0. So when k is greater than or equal to 0, it assumes the value of 1. Now, u of n minus k minus 1, what values of k, again, this is a sum over k, so we need to think about k values. What values of k will that be non-zero? The way I approach this, as I suggest, is like you set this inequality up. You ask your question, when is the function n minus k minus 1 greater than or equal to 0? And you're asking for what values of k that inequality will be satisfied. Well, k is negative, so you have to multiply by minus 1 and reverse the inequality direction. And then you put n and minus 1 on the other side. What you get is it'll be 1 whenever k is less than or equal to n minus 1. And then we stop. We stop and then we think. This function starts or allows non-zero values when k is greater than 0. This function allows non-zero values when k is less than n minus 1. And you ask yourself, what could be the bounds of this summation? 0 to n minus 1. Exactly. The product of these two things is going to actually require that k is only going to be 1 when k is both greater than 0 and less than minus 1. Because this product, if either one of the terms in the product is 0, the whole product is 0. Right? So the product u of k times u of n minus k minus 1 will only be 1 when k is greater than or equal to 0 and less, like think of it as a logical and, like they both have to be 1, right? And less than or equal to n minus 1. Because of that limits on the values that are put out from this product of step functions, we can write down our summation differently. We write it with k starting at 0. I know this is small. We write it with k starting at 0 and going to n minus 1, and this simplifies our sum. Work is not yet over. What do we have on the inside here? Well, we've got k's and n's and all sorts of stuff floating around here. The first thing that we notice is that this summation is over values of k. What does that mean about 1/3 to the n? You can take it right out in front. In fact, I take 1/3 to the n minus 1 out in front. It is not a function of k. It is a constant term in all of these sums. Right? K is changing. 1/3 to the n minus 1 is always there. So I'm going to factor that term out. Okay, then I write it as 1/4 to the k times 1/3 to the minus k times 1/3 to the n minus 1, and then I take that 1/3 to the n minus 1 and I move it to the front. Okay, now these two terms are functions of k, and one of them has a negative power. I want them to have the same sign for the power. So I take 1/3 to the minus k, and I write it as 1/3 to the minus 1 to the k. Can I do that? That's right. This is an important algebraic property that a lot of people forget, but if you don't remember it in DSP, you will be punished repeatedly. A to the B to the C is equal to A to the BC. So this is 1/3 to the minus k, and I can write that as 1/3 to the minus 1 to the k. It's the same thing. Same thing. And I do that because I want to write 1/3 to the minus 1 is actually 3. And so that's exactly what I do. And I write 1/3 as 3/1 to the positive k. Now I can combine, these are both to the k power. So if you have a to the k times b to the k, that is equal to ab to the k. Algebra again, that means that I can merge this stuff in, and I get 3/4 to the k value, k power, and then I have a sum from 0 to n minus 1 of 3/4 to the k. And I can apply the finite sum from 0 to n. In this case, it goes 0 to n minus 1. In that case, you just plug in n here, not n plus 1, because the top limit is actually the value n minus 1. Does everyone follow that? Okay, just be careful about plugging in, like, this is n plus 1. So if this thing is n minus 1, this thing ends up being n, not n plus 1. So in this case, I have an n minus 1 in top, right? So I plug in here and I take the value is 3/4. So applying this equation, I get 1 minus 3/4 to the n over 1 minus 3/4. That's the result. And if you were to simplify, and that's what you see right here written out. That's the solution. So 1/3 to the n minus 1, that's still out in front. So that's still out in front. Over multiplied by whatever the result of the summation is using that geometric series formula. 1 minus 3/4 to the n power over 1 minus 3/4. And that's times u of n minus 1, because this signal only starts from, we're actually plugging in n minus 1 here, right? And so the output is non-zero for n greater than or equal to 1. So we restrict the solution to values of n greater than or equal to 1 by multiplying by this u of n minus 1. All right, we're right at the end of class. So we'll stop class right there. I'll stop the recording. And if you have questions, go ahead and ask them after class.
You know, his